Okay. Um, okay, so let's start. Before moving on to this discussion, I want to tell you all that this will be a interaction kind of thing. First, I will discuss something what I know and describe both mathematically and with demonstrations as well. But then after that, you guys have to interact with that and you have to write a little bit of code. Okay. Now, before we begin, I want to know how many of you actually know Python.
Yeah, maybe you can like raise your virtual hands or yeah, okay. Cool. I think maybe more than half of them know Python.
Yeah. Okay. Yeah.
See a lot of
So
hands.
then it's fine. Okay. Okay. So today's the purpose, the whole purpose is we want to introduce the subject in a way that new people comes and it gets insight about what is it and we want to do this and have feelings about how do we do physics, especially those equations which are very difficult to solve analytically. How do we solve and what are the exactly issues we face by solving it on a computer, and we will see a lot of problems are there which we are still not able to solve. Okay. So here's a bird view. What we'll be doing today. First, we will get introduction of this thing. Um, Wait a second. Okay, let's go. Okay. Um, so today we will get introduction to Monte Carlo simulations. By the way, there is a kind of definition like what exactly you count as a simulation and that kind of thing. I'll discuss that later. Okay, and the second thing is um, yeah, okay. Then the next session we are planning to do molecular dynamics, in which we will be simulating a noble gas inside a box, and that is our ultimate goal actually. And this session is a prequel of that. We need certain kind of tools to do those problems on in molecular dynamics, and we are trying to introduce those tools today. Okay. Um, and I will describe you few problems which we encounter in this, and I will show you like what are the better solutions in future which we are still trying to develop. Okay. um, okay, I think you know Python and you know this calculus kind of thing and physics, so, and if you know Jupyter, this should be good for you. Okay. uh, so what we'll be learning today, the first thing is when we try to write equations of natural phenomena on computers, most of the time we have continuous variables and we have rational numbers. And the problem comes where we store numbers in memory, and memory has a certain finitism thing. Okay, and we get an what do you call a limit as to what you can simulate and how accurately in which in what time you can simulate it. And so we will be looking at how to actually and how they are storing numbers in the memory. Okay. The second thing, very important thing, the random number generators. Uh, we will trying to we will try to understand what exactly is randomness. Okay, and how do we generate it on computer? Because computer is kind of deterministic machine, and we are trying to emulate some kind of random or chaotic or stochastic thing on a deterministic machine. Okay. Um, okay. Then, as an example, I will do this pi computation. I will do certain integrals, and then you guys have to do one integral. Okay, cool. Um, Here's the second thing, but we'll see that later. Okay. Okay, guys, if you want to play along this thing, you just go to this link. I'll send you the link, and please don't use the same notebook I'm working on. Just copy the notebook. When you type this, wait a second. How to um, send the message? Uh, 1 second.
Yeah, the chat box is probably invisible for you, but if you send it to me on Telegram, I can share it. If you have
Okay, I'll
Telegram.
send you on Discord.
Yeah, that's fine.
Okay. Okay. When you open that link, you will be directed to here, and uh, I want you to copy this MCXYZ file, duplicate it, and rename it, and then use your file. Don't use this file because I'm working on that. Okay. Okay. Um, okay. Did you guys get the links?
Yeah, I've shared the link.
Okay. It will ask the password, and password is 1969. Okay. Okay. So let's start. First of all, before we begin, I want to. Okay. Before we go forward, first of all, let me tell you that the most of the work we'll be doing today will be based on random numbers, and we need to have a very intuitive grasp of what exactly is random numbers. Okay. 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 Damn it. Okay. So we want to define a variable. Okay. Before that, why is it going like this? Okay. Okay. Here it is. So we want to store the rational numbers on hardware memory, and we want to represent the numbers which we write in mathematics in terms of power series, and the power series of base 2, of course, and want to store it in bits. Okay, and so suppose we have n bits, then how many numbers, I mean, how many different numbers we can store in that. Uh, if we take first bit as for the sign, okay, whether the number is positive or negative, we store the first bit as a sign, and other other n minus 1 bits which are which we use to store the number. Now, I think you guys all know what these things are, but be aware that k, you might interpret k as a 10 to the power 3, but in binary it is 10 to the power 10, and this is the progression. It goes 10, 20, 30, 40, and we will be dealing with this series and not this. Okay. Okay. So how many ways, sorry, okay, how many ways can we represent a number on a machine? Okay, so it highly depends on the architecture of the CPU. Okay, but generally there are fixed point numbers, there are floating point numbers, there are addresses, and there are other few types of those, and we will be dealing with these two types of numbers today: fixed point numbers, and the floating point numbers. Okay. um, um, okay, so I assume you guys know a little bit of how architecture of computer works, but let me tell you in a little bit that each architecture has its own instruction set, and which we call as a word size of those word size of those processors. Okay, and in older days all those word size used to be 8 bits. Okay, so what happens is if we want to store one number, okay, we can store at we cannot store less than 8 bits. We have to use one word or multiple of the one word. Okay, so in older bits days we used to have 8 bits for one word. And just imagine how many different numbers can we store if we have 8 bits. We can store to the power 7 because the first bit we'll use for the sign. Okay, so sign, so plus and minus, which gives you two different numbers, and then remaining are 7 bits, so we have 2 to the power 7. Okay. Okay. So today, most of those Windows PCs we use today, this Intel things, it actually comes with x86, which it says we can use 32-bit and 64-bit together. Okay, but in 64-bit processors, if we write numbers, we have 63 bits left. First bit is of course sign. So what does it mean that we can write 2 to the power 63 numbers? When we convert it into decimal, it turns out to be 10 to the power 19. And you know how this works. It works because of this. Okay. Okay, this is fun story. In old days, what used to happen is there were so many companies building their own computers and machines. Their own the various languages used to exist there. Programmers used to write their own uh, representation of numbers. They will define like how they want to represent the numbers in the memory. And so different machines, different language would have different things. So of course we need a one standardization of the representation, and which is done by IEEE. It is called something like 274 or something. I don't know. Okay, so okay, we want to store reals or rationals on the memory, which are in in the form of either fixed numbers or floating numbers. Okay, and if we have fixed point numbers, what we know is okay, how do I write here? Wait a second, I need to type here something. Okay, so what happens? We have a number. For example, we have suppose in decimal number we have something like 137, right? My favorite number. Okay, so what is it like? It's 7 times 10 to the power 0. Okay, uh, this is 3 times 10 to the power 1, and this is 1 times 10 to the power 3, right? So we go from 0 to 1 in this direction, okay, and create numbers, build up numbers which are bigger than the previous one. But if we go this side from 0 to -1, -2, -3, we get a decimal numbers. Yeah, so those fractional numbers or real number or rational numbers, okay, uh, 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 depending on how many decimal points, how many significant numbers you have. Okay, now suppose okay, if the number has finite number of points after the dot. Okay, uh, um, so suppose we have x dot y. Okay, so this x is some number which is in the power series of either decimals or binary, but it is 2 to the power I, and which where I belongs to natural numbers. But if after the dot we have the power of those numbers negative, and the coefficient determines how much smaller that number going to be. Okay, so this is the normal way we will represent it mathematically, but not on computer, of course. Okay, I mean there are caveats to it. Okay, um, okay. Now, if we represent certain numbers in this way, uh, what is the underlying error here? So what does it mean to have an error? We have a number, for example, I don't know how to give, like 3.14, for example, right? Um, we know that this is an erroneous number if we call it pi, right? Because we know other decimals are there. So we are truncating these red decimals and just taking these things. We are taking a finite chunk of the whole representation of mathematical number, right? To store it in within the computer hardware. Okay, so what happens then? Um, we this is the number we store, and the highest order which lies here we call it error, right? Now see here, we got sign here. This is the first term, okay, which says some coefficients. And by the way, in computer, when we store bits, we don't care about these powers. We only care about these coefficients, because the powers to the power 2 to the power something is just understood. Okay, um, this is 2 to the power 0. Okay, so okay, what um, okay, yeah, okay. So we know that how many numbers there are before before this point, before the decimal point. Okay, we of course know it, but the only problem comes after the decimal points. If certain numbers doesn't have a ending point, right? It just goes on, or maybe it is longer than what we can store within the memory. Now, what we can store in memory depends on architecture. Suppose we got a got a 32-bit machine. Okay, then in 32-bit machine we store it this way. Okay, we have 32 bits. We use 23 bits for mantissa, 8 bits for exponent, by the way, and for the 1 bit for sign, right? Now what is this plus or minus something? Okay, uh, uh, sorry, okay, sorry. Okay. We got exponent and mantissa. Okay. So here's the thing. In scientific notation, we write numbers like, for example, if we got speed of light, we write 3 point what 2997992 or something. So you write 2.9979245. It's okay. It's of course a ending number. Okay. The last digit is 8. Okay, and you write 10 to the power 8 or something. We write 8, right? Correct me if I'm wrong. Okay, okay. So what happens is this 10 to the power something, this is written in exponent. Okay, this is mantissa, and the sign of it is stored in 1 bit. Okay, and this is the order, this is the particular order we store in the memory. And another thing to remember is the mantissa we store it is and in a, so suppose we got mantissa in a bit like 1010. No, okay, 1001, suppose. Okay, why is it symmetric? I need to take something asymmetric, like okay, 110001. Okay, if this is mantissa, the way we store it in memory is the reverse of it. So you get the idea. It will be stored as 10011. Okay. Now another problem with machine numbers is okay. What is machine number, by the way? Okay. In mathematics, you know that all the numbers we build up from the natural field. Okay, we have the field of natural numbers. Okay, then we're using some Peano axioms and all those kind of things. We build up R. Okay, and then we go further and we build C. But we want to store only real numbers on the PC, right? And the problem is real number is like this, continuous. Okay, but in computer we got a problem. We cannot store less than. Okay, this is 0. This is minus infinity. This is plus infinity. Okay. Um, okay. So we got this kind of limit. We cannot go bigger than this number. Neither can we go bigger than this number. Okay. And nor can we go less than these two numbers. So we lie somewhere here. We lie somewhere here. Okay. Now we still have caveat within these numbers. Okay. What is it? It is this. We got a discrete parts here. We can only store those numbers, not all of those. You get idea why? Because rational numbers are like infinite between 2 points, and we cannot store all of those here in PC or any machine we build with the computation which is based on the theory of uh, um, computation built we got introduced by Alan Turing in 1930s 40s. Okay, if we want to do certain beyond that, we need some computers beyond this Turing machines, right? Okay, now here's the thing. Because of this finitism, we get to store only these numbers. Now, for example, what if I want to store a this number? I want to store this number. What do I do? Of course, you have to truncate it, either this side or this side. It depends uh, on what is the scenario you are using number for. Okay, okay. So I call this M set for all the machine numbers we can store in machine, which is very tiny set of the reals. Okay, very tiny. The cardinality of this set is very small than the cardinality of this. Okay. Okay, there are some words for this. If we got numbers less than this or less than this, we call it underflows. And if we got numbers bigger than this, we call it overflow. Okay. Uh, but here's the thing: when certain while doing some computation, we know what is the value of certain variable, or whether it is in memory or register or whatever. Okay, if it tries to go beyond this, okay, it goes below this, we know it is going to underflow, right? So this kind of errors we can solve actually, but just by setting that variable equal to 0. Okay, simple. But what happens if it tries to go beyond these two numbers? Like it is trying to go beyond the limit of the machine. Okay, of course nothing will happen, but most of the time the execution of the program just just shuts down. Okay, it hangs. Okay, because you get the idea, because we have a number. Okay, let me give you an example how to clear this. Okay, um, example is simple. If I got 3 plus 1, by the way, 3 is integer, right? 1.0, which is float, times 10 to the power minus 3. What happens if I want to add these two numbers? This is a floating point number and this is a fixed point number. Um, what what exactly happens within the CPU? Okay, what it tries to do is it tries, of course, it cannot add these two numbers because it needs to have two exponents same. And in order to do that, what it does is it tries to reduce these exponents in such a way that it can match to this. And in a way, when it does that, it has to um, do manipulation of these numbers, and it shifts the bits. And when it does that, what happens is, suppose we got some digit like 001, right? So if he wants to lower the number, it adds 0 again. It keeps adding 0 and 1. Now you see this number getting smaller and smaller. But what happens is, suppose we got a 8-bit processor, right? So in 8-bit processor, or even in a 32-bit processor, I will show you in next, that we can get accurate numbers after decimals up to 6 or 7 decimals after the dot. Okay, uh, if we go beyond that, well, it's just overflow. Okay, so what if my number is bigger than that decimal, right? It just truncates it. Now that's an error, right? Because my computation gets wrong. This has to be counted, but it doesn't count because it doesn't have capacity to do so. Okay. um, okay. Uh, to okay. I think most of you guys know this, like what are the data types and how do we store it and how many words do we need to store those. By the way, it depends on machine and programming language we are using, but yeah, generally this is the table given by IEEE. Okay, I just copied and pasted here just for the reference. Okay, now here's most important thing. What happens when we, okay, when we are storing this floating point numbers. uh, I just talked about uh, the fixed point numbers, but in floating point numbers, we got exponent here, mantissa here, and sign here. Now, you see some bias thing here, okay? Uh, the architecture, the way people has done this kind of things is that we want to just add two numbers, x plus y. Okay, even though the y is negative, we just want to add them, and we don't want to store it as a negative number. Okay, because it we need more kind of complexities in there. So what it does is we introduce the bias, and bias is usually the number. Bias is usually number equals to uh, the number of possible numbers we can represent with our bits. For suppose we have 8-bit processor, then we have total number of 7, right? And 7 by 2. Okay, this is the number mostly we take as bias. And if it is 32-bit, uh, uh, we take 31 here upon 2. Yeah, okay. Okay. Now we know how to store the numbers and all those things. Now what we want to know next is uh, what is precision. Okay, like whenever we are trying to, okay, as a scientist or as a computer solver or whatever you're doing, you need to know that what is the minimum or maximum number you can store for your machine. And um, uh, and there is another thing. Okay, I'll which I will tell you in later. Uh, for now, imagine that I just told you that if we just do this kind of thing, like 3 plus 1 times 10 to the power minus 3 or maybe here some bigger number, maybe 8, okay, and here also 8, okay, this is -8, okay, and we just got a 32-bit PC, okay, 32-bit processor, which we know will just give us 6 to 7 decimal points after the dot, okay. uh, uh, so we got 1-digit overflowed here. what what is the consequence of it? Okay, the consequence of it is that um, uh, we don't get the number which we want. It gives the numbers which is not even it's a okay, sorry, what happened? Wait a second. Oh, my notebook just gets shut down. Okay, till then we can discuss here. Okay, last bit or last few digit gets overflowed, and the consequence of it is that sometimes when we do this kind of things, 8 plus 10 to the power -8, what we get is equal to 8, which of course is not true mathematically, and that is not what we want in computation. We want certain kind of accuracy, though we cannot get the exact number if we don't have enough processor. Okay, now we have 64-bit, but uh, okay, in 64-bit we can do that, but if we got lower than that, that would be a problem. Okay, so okay, and we will be doing these all things in Python, and I just got to know this fun fact about this, that Python doesn't support 32-bit floating point numbers, and the way IEEE defines 32-bit numbers, which it says, so we have this notion of single precision numbers and double precision numbers. Okay, so maybe I have written here somewhere. Okay, yeah. So single precision numbers are 32-bit words and double precisions are 64-bit words. Now, what happens here in Python is um, IEEE defines um, uh, single precision as 32-bit and double precision as 64, but Python doesn't even have single precision thing. It just uses 64-bit for all the calculations, okay, which is kind of good if you feel, it feels like good, but not in all scenario. Okay, um, um, okay, I need to run this, but for that I have to restart my server. Just wait a second. Okay, okay. Okay, I told you that there is this limit of a number. So here is this number. Okay, where is it? I just read. Okay, it just went out. Okay, so we got this reals. Okay, we got this limit, and this is 0 is somewhere here. Okay, these are smaller numbers. We cannot store beyond these. We cannot store beyond these. We cannot store within these. We only can store these. Now this number is known as machine epsilon number, or epsilon m. Okay, and Uh, okay, and it is for 32-bit machines, it is usually of the order 10 to the power minus 7, which I just mentioned before, right? That it will give us 6 to 7 decimal points for 32-bit points, 32-bit machines, and for 64-bit machines, we will get 16 or something decimals. Now, compare these decimals to what we study in physics. Okay, we got 10 to the power minus 19 or something. Okay, we got 10 to the power 20, 23 for our Avogadro thing. Okay, this is like charge. Okay, we got the gravitational constant 10 to the power 26. How small these numbers, how big these numbers are compared to what we can compute on our processor. Okay, so this is a big issue. Okay. Okay, now I just used NumPy to get this epsilon from the machine, but here I want to show you exactly how to calculate epsilon by our hand so that you get the idea what exactly it is epsilon. Okay, so I'm doing this um, uh, loop like forever, but not forever. Okay, I initialize n equals 1, and I say, okay, let's assume epsilon is 1. Okay, and I run this loop, and I divide epsilon at each loop. Okay, so I got 1.0, I divided by 2, I got 0.5. Okay, and in this equation, we just saw that machine number is actually that number, or machine epsilon is that number when you store a number one, okay, the representation of number one in memory, when you add this epsilon to it, uh, it doesn't change at all. It remains one, right? I just give you the example and you get the idea, okay? So if we go a little bigger number than epsilon, then it does changes the number one representation in the memory. But this is the number uh, 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 which is very important to understand what is the capacity of your machine at all. Okay. Um, okay. So you get this thing. I divide this epsilon in each loop, and this LHS is left hand side, which is actually this left hand side. So 1 plus epsilon, I calculate 1 plus epsilon here. Okay. Uh, and I print at the end of loop. Well, uh, I increase the value of n by 10. So what I get result here is this. So if I calculate this, for example, 21 times, I don't know why I'm getting 21. I was supposed to get like in the multiple of 10. Okay. Is it running? No, that's wrong. Okay, issues here. Let me restart it. Okay, leave it. Okay, so you see this epsilon value at each at every 10 iteration, the left hand side is getting converging to 1. Okay, that's what I'm trying to check it. If the left hand side converges to 1, then I break the loop. Why? Because when left hand side becomes 1, it means I have reached the value of epsilon. Okay, uh, and okay, yeah. So now you see the epsilon getting converging to certain value here. So after this many iterations, I get epsilon equals something order of 10 to the power minus 19. Okay, we just calculated this by our hand, and this is what numpy is giving us, which is giving some order of 10 to the power minus 16. Okay, and we got 10 to the power 16. Okay, we got 19 actually, but if you see the number for left hand side is 1.0 exactly for 10 to the power 19, and the numpy is saying 10 to the power 16, and for 10 to the power 16, we got the number 1 point something 00 and at 4 at the last. Okay, so somehow we got better than numpy. I don't know how. Okay, uh, uh, so this is the number. Yeah. Okay. If you try to add smaller than this number um, to this one, which is the representation of mathematical one in the memory, you will always get one. Yeah. Okay, and if you try bigger than that, bigger than this epsilon, which you see here, if we try bigger and bigger, the one gets changed. This is the meaning of epsilon. And why we are doing epsilon, why we are finding epsilon, because epsilon, machine epsilon, is a way to communicate to others that what is the capability of a machine. Okay. Okay, now let's do some computational physics. Okay. Uh, um, now what kind of errors can we get while doing computational physics simulations? Okay. The first, of course, important thing is Fallacious theory. Okay. Uh, this is natural, right? So natural is like when you are simulating your code on certain PC. Okay, that PC has its own circuit or motherboard. Okay, it has got his environment. It has temperature. It has some randomness within his circuit because of current and temperature and all. Okay, these might affect the bits in the motherboard. So it is very rare. Okay, but the most important thing is this third and fourth. Okay, which is mathematical errors and computational errors. Mathematical errors are actually intended errors, okay, which are not like, okay, we didn't wanted it, but it came. Actually, these are the errors we impart on our equations. How do we impart those things? So suppose we got a function, uh, uh, some function like f of x, okay, we know that we can expand it with Taylor series or maybe Maclaurin series, whatever you prefer. Okay, uh, uh, like it's uh, this thing upon I factorial. Yeah. Okay. Uh, so we and this goes to infinity actually. Okay, then only it converges to f, and of course this is only for certain functions and not all class of functions in reals. Okay, but so we take n here, so we take only the small part of the whole series, and therefore we get this mathematical error. But the most important error here is this computational error, which is caused by aforementioned all. I just mentioned all those things. We can have this epsilon kind of thing, memory kind of thing, which numbers can store and all those things. These introduces an error which we call computational, or you can call round-off errors. Okay, and these are very much important. Okay. Now, before I go to RNG and all those things, uh, I want to ask you a simple question, like how many of you recognize this equation? Can you just raise your hand, please? Okay, we got uh, two people. Okay, three. Okay, so at least we know we have people who knows integrals, right? So I think I'm sure most of you guys know this equation. So we have f of x from this is first dimensional integral. Okay, we are trying to and because you have done some integrals, you know that not all integrals are easy to solve, right? Okay, so and it's not about easy to solve kind of thing, but some integrals are actually analytically impossible to solve. Okay, uh, so we have to solve it uh, computationally, right? Uh, and this is the way we write Riemann sums. Okay, uh, now okay, how to stop this? Okay, um, okay, let's try to, this is pretty straightforward. All of you know this maybe, or maybe few of you. Let's try to write a code for that, and I got a code for that here, which is very just few lines, and you get the idea that we are trying to, this is the length of the domain over which we are trying to find the integral. Okay, and uh, if some of you guys recognize the what is this, what exactly is this, um, uh, okay, I think this has some error here. uh, okay, there has to be, and here um, okay, now you see that this thing, or at least this is actually average of a discrete function. You see, isn't it beautiful that when you take these two down here in reciprocal, this is an average of a continuous function, which is equal to a average of discrete function in a limit tends to infinity. Yeah. So why I'm telling you this, because what we are going to do further here will depend on averages. You need to know uh, averages, and you need intuitively you should understand uh, where averages works out. Okay, and I want to give you a feel for that. But before that, uh, here is the Riemann integral which I wrote here. Okay, and I'm trying to solve it. Uh, Simply sum equals sum plus f of x naught plus ih, where x naught plus ih equals to xi. And you should know why, because so we got this Cartesian space, we got this some function. We want to integrate from here x naught to x. Okay, and we divide this domain in discrete chunks, and the size of this is h. Okay, and the number of these chunks are n, uh, and we ask the question, what is the average of this function within this domain? And we kind of see it is somewhere here, right? But of course we need to calculate it. Okay, um, so that's what I'm writing here. You see this x naught plus at each iteration, I'm going to this next IH. So I'm stepping forward H step at each iteration and reaching here. And at each iteration, I'm evaluating the function and adding it to the sum 0. So I'm getting the area here, which is kind of integral. Okay. Uh, um, okay. Let me show you what. Okay. So I'm taking a function 4 upon 1 plus x squared. If you have done enough integrals, you know that 1 upon 1 plus x squared is actually some kind of bell curve, right? So it is some kind. Okay, here it is. Okay, 0. Okay, so this is some kind of bell curve here, and this 4 just says that how we stretch on the y-axis. Okay, so we got this bell curve, which we already know the solution for this integral, so we don't have to solve it. But I'm taking this function as to show you that if we don't know the analytical solution of an integral, uh, how are we going to solve it? And to do that, I have to take an integral of which we know the answer already, right? Okay, so if I run this thing, before that I need to run this. Okay, that is it. Okay, so I run it. Okay, I'm running only this function, and you see I'm calling that function here. Okay, here integral Riemann. There it is. Okay, now what I'm trying to do here is I want to see the behavior of this integral as I increase this number of chunks. So I do for n in this the multiple of tens, I do this thing, and I calculate the integral. You see it converges to 3.14, which is actually pi. Okay, and here you see what is an error. Okay, how do I know what is an error? The error I know because I already know the value of pi, which I take from the inbuilt math package of Python. Okay, and because I know analytically that the integral 4 upon 1 plus x squared is equals to pi actually. Okay, so I know the actual value, and I'm trying to see that the value which I calculated over this function, what is the absolute difference between those two, and those differences are here, and you see the difference is decreasing. Okay, yeah, I get it. It is very slow actually. You get idea because at each step it is decreasing only like one step to lower in power of 10. Okay, which is kind of very slow. Okay, for what we want to do. That's why we want to do Monte Carlo. Okay, okay. So now you get the thing that this is the pretty much what we studied in high school. Okay, we know all these integrals, how to solve it, and what is the error. Now what we want to do is we want to introduce a method for which this convergence gets very fast to pi, and this error uh, 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 turns out to be getting tends to 0 very rapidly instead of this one step. Okay, but to do this, I need to introduce this concept of uh, okay. You see what we did here to integrate this function. To integrate this function, what we're doing is we are evaluating the function at discrete points in the domain. Now the new idea is what if we try to do it at random points. Okay, now to give you an intuition, let me first you need to understand this equation. What is this equation? Okay, uh, so what I claim here is this integral is actually okay. So if we got the function which is one dimensional function here, Okay, then integral represents the area, which is like a two-dimensional space number, or you can say a space occupation in two dimension, right? So if I got a function which is of d dimension, okay, then what does it mean to integrate it? The integral of that d-dimensional function is actually d plus one dimensional space occupation number, right? Okay, and as I just told you, and here you can also see that thing, that this is this is one plus one, see, two-dimensional space number, which is area, and here it is one dimensional space, which is length. Okay, so area and length is associated with the average of the function. Okay, uh, so I generalize it, and we say, okay, we got d-dimensional function, we want to integrate it, and when we integrate it, we get a d plus one dimensional space number. But here on the right hand side, on the based, sorry, okay, so I got this d-dimensional volume, which is actually the domain of the integral we are trying to solve the integral over. Okay, and here is the average value of function. Um, how many of you actually see that this is actually the average value of a function? I just want to know that who actually doesn't see that this is not an average or is an average. So I pose the question again. How many of you see that this is actually an average value of a function? This circle. Okay, cool. Abhinandan Paul. Okay. Uh, um, 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 okay. So now what we do is we ask the question. We want to find this d plus one dimensional volume or space number. We know this d-dimensional space number because it is actually the domain and it is given in the problem. So we just need to calculate this average. And our question will be, how do one calculate this average, right? Um, um, well, there are so many ways to do that, and that's what the whole subject of computational physics is. Actually, numerical analysis, you can say, okay, but in computational physics, we use these techniques and try to simulate these physical phenomena in such a way that it at least gives us an important result. Because here's the thing, we cannot simulate. Okay, let me give you an example. If we got a box, okay, we have a box and there is a gas within the box, we have a lot of particles within the box, okay, and one says, okay, I want to simulate the thing, how what happens, what happens, how it happens, when it happens, kind of things. Okay, so what do you calculate each and every variable for all the particles? Okay, because how many particles did you get in the box? Um, we know usually we take the gas or liquid in terms of mole. Okay, and you know 1 mole, uh, you know, proportional to Avogadro number, which is like 10 to the power 23. That many particles we got in a box. And we just saw that 10 to the power 23 is just beyond our computational capacity of 64-bit computer. You see that? Where is it? Yeah, here it is. Here, you see. Um, then, um, okay. Okay, then what do? We take samples. We take samples of the whole population of these particles within this box, and we do computation on that. Okay, and this is essentially what Monte Carlo is. I will describe a little bit deeper in Monte Carlo later, but before that, I want to dive onto. Okay. So I said we want to evaluate this average value, but how many ways we can evaluate the average value? Okay, of course there are simple ways. So okay. So first thing is just simply do this thing, like how many functions we are evaluating, just add it up and divide how many times you are adding it up. Okay, that's what this essentially is. So that is Riemannian sum, right? Okay, but here's a new thing, that let's, instead of evaluating function at every point, or finite number of point within the domain, let's take random points within the domain, evaluate function at that point, and take an average of that function. So and do this multiple time. So we got this sample, okay, and we do it statistics on that okay, I got this. So when you do this random number generation, when you generate a number within the domain, and you say, okay, at this point this is the function value, okay, and you add it up, you average it, and you say this is one Monte Carlo simulation. Okay, and you do the next simulation, you do the third, you do fourth, you do fifth, you do thousand of such things, such simulations, and then average it up, and then you know that is the exactly, or no, at least approximate solution of the integral. Okay, so before we do that, we need to understand random numbers. How do we generate random numbers? Okay. Um, okay. So we got so many types of random numbers. Actually, I don't even know all of those things. Okay. But the ones which I like are these three types. Okay. First is atmospheric noise. Okay. Actually, when you were okay, I don't want to describe that. Okay, just get the idea, and you can search on Google what is atmospheric noise, and based on that you get random numbers. But this is very important. The second one, you know that when you throw a light or photons on on uh, on a um, mirrors, right? There are some probabilities in quantum mechanics that whether it will go through or reflect back or that kind of thing. Okay, based on that random thing, which is actually the natural randomness. We are not simulating the randomness. That is a natural way to get the random numbers, right? Uh, so that is kind of thing. And if you want to see, uh, okay. They've got this kind of chips here. Okay, we can just plug in USB as a USB thing and use it just to generate the random numbers uh, for for these kind of things. You see, okay, and I haven't seen anybody's using this, but of course we are still in university, so we don't know how people are using it. But uh, uh, I know one application where these things are very important, which is cryptography and cryptocurrencies kind of thing. You need a machines and crunching numbers at every second, doing things on the blockchain, and they need these kind of things, and they buy these things. Okay, uh, how do you get a random numbers? Okay, if you want to get it. Okay, I suggest using this. Okay, so in every Linux system, we get if you know the Linux hierarchy. Um, okay, let me show you. Okay, so in every Linux system, you will see this kind of uh, um, file system in a root. Okay, so this is a root directory, and when you go to the device things where we mount all those devices coming out of um, uh, CPU or motherboard, external devices or internal devices, and there is one device called DEV called random, and there is another one. Okay, let me show you that. Okay, you see this? Where is it? Okay, here is first random device, and here is another you random device. The way it works is you got a PC or you get a laptop, whatever you got. Okay, it has a motherboard. I just told you it has this temperature kind of things in the machine. Okay, sometimes it hangs, sometimes it doesn't hang, sometimes it goes smoothly. Sometimes it's very hot in the motherboard. Fan is just running, so it's kind of chaotic thing. Okay, um, and it we got an entropy. Okay, if you study a little of information theory, okay, so we got this uh, entropy of things surrounding the PC. Okay, now what there is this device. What it does is it takes those kind of environment variables and turns it into a uh, random characters. Okay, so um, and it stores in random. This is the most random thing you can ever get in Linux system. Okay, you don't need to use any Python or any library. They also use this inbuilt random device. Okay, but this has some issues because entropy is a kind of uh, you know hard thing to gain from, because sometimes you don't have access to laptop. You're not using laptop all the time. Okay, so you're not getting entropy all the time in your machine. So what happens is whatever it got or certain times it got some random variables. I can show you what kind of thing it has. So if I say right head, for example, I just print the first line of random device. Do you see this? Do you count this as random or not? Of course we do. Okay, uh, this is the most ever random thing you can ever get on Linux system. Okay, but if you ever want to use things, I recommend using um, uh, urandom, because this random thing is directly coming from this noise you are getting from hardware and temperature and surrounding things. But this so you sometimes you don't have entropy. Okay, but this urandom takes care of all those things. Okay, even if you don't have entropy kind of thing, it hashes your strings and produces new strings which seems random, and so you can use it all the time. So I'm just giving an example, like there exists this kind of randomness within our PC, where these softwares and inbuilt software, they use these kind of things to generate your password or to MAC address or whatever, like IDs or unique IDs or so many things there are to do these things. Okay, to secure your network. Okay, now uh, okay, um, there is this okay, these are all natural. You see this? Okay, these are all natural things. Okay, I just forgot to show you that. I told you this: if you use random device, which is it is natural random number. Okay, but when you use this random device, it is actually not natural. It is pseudo random number, because I told you that sometimes you don't have entropy, and somehow I have. I don't know how. Okay, and so if it doesn't have, it has these strings and produces new string. Now, as a result, you are using a hash function, and hash functions are not that secure. Uh, if you are wanting to store information for like more than century or so, okay. Uh, um, yeah. So this thing is a pseudo random number. Is there other ways to generate pseudo random numbers? Because uh, we want to generate new random numbers mathematically. Okay, because okay, so when you whatever language you're using, Python, C, or JavaScript, or whatever, there will always be this function called random. Okay, and you need to read the documentation where you can find it. Okay, uh, and there are so many types of random numbers. We can have this whole 1 year uh, course on random numbers. It is that much big course, that much big subject it is. Okay, but in short, I just want to uh, give you an intuition what we might call as random. Okay, so if you guys know a little bit of modular arithmetics, okay, uh, what is a modular arithmetic? So um, we imagine certain kind of rings here. Okay, so suppose and I draw some discrete points on that. So first point, second point, third point, fourth, fifth, maybe 6 point. Okay, and then what I do is I say, okay, this is 0, 1, 2, 3, 4, and 5. Okay, um, then what is this? This is 6, 7, 8, 9, 10. I think most of you guys know. Okay, you just keep going on just like clock. Okay, and the numbers coming out of this field, if you have studied field theory in your mathematics, you guys already know that this this modular arithmetics actually is under closure of a field, under addition and under multiplication. Okay, and we use it as a random. Why? Because see here, um, uh, okay, I'm taking this modular of 9. Okay, so let me okay, I got these 9 points. Okay, here it is. An equation you can find somewhere. Where is it? I don't know. Okay, okay, this is equation actually. Okay, uh, okay. So this M represents in which modular ring we are working on, and this ax plus c is kind of some constant variables. And you see this is a recursive formula. Okay, uh, uh, what happens is if you take this ninth modular ring, and if you say, okay, I want to take um, okay, whenever we generate random numbers, we need a seeding. Okay, we need to say, okay, where to start. Okay, because these are pseudo random numbers and we want to generate it, so we need an algorithm, and this is an algorithm. Okay, so we need a starting point so that I can put value here and generate the next one. Okay, and that is called a seeding. Okay, so I say the seed number here is 0, suppose. Okay, so here is 0. Okay, um, uh, okay, so here is 0. I added 1 to it, but multiplied by 4. And you see, you do that. Okay, edit 1. Where is 1 here? Why is it showing 1 here? Okay, this is 1, 2, 3, 4, whatever. 3, 4, 5, 6, 7, 6, 7, 8, right? Okay. Um, okay, so I got 1, and then what I do is double it, I go there, or maybe whatever number comes here in this equation, it sends us to the next number. Okay, okay, this kind of things it does with us. And imagine doing this thing going on further, and um, if you are in within this ring and working on and then translating it back to your decimal ring, then what happens is it sounds random number. Okay, it looks like a random number. To see it, you I'm doing this. I'm making this function. Okay, this I'm taking seed 0, A419. I just say this here. Okay, these are this is just I'm storing it in array. Okay, now I want to show you is okay, no, here's the thing. whenever we draw this ring, we got these numbers here, right? Okay, and I said that uh, if we start from here, we will get here, then here, then here, then here. We will get it randomly to all these numbers. But after a certain period, we will start repeating it. You see that? Okay. So there is this. Okay. So suppose 1, 5, 9. Okay. 7. And again, it comes 1 and 5. So this is a random number. How can you say it is random? Okay, there is a way to taste it and those kind of thing, but it is like small as okay, so it got a length of 4, you see. Okay, but of course it's not important. If we want to generate it really randomly random numbers, you need m, which actually represents this length of this random sequence. You need it very big, right? And okay, something happened. Okay. um okay. um okay, so here I'm printing the length of that thing. Okay, I'm printing that by taking these values in this thing, in this equation, what is the length of this sequence I get uh, as a random sequence of numbers. Okay. uh, um, okay, I want to run it. Let me restart this thing. Just wait a second. Okay, let's run it again. Where we were. Run this. Okay, so I run it, and you see the length of this random thing I get is 9. And if you want to see what are those random numbers, let's see it. Okay, you see 1, 5, 3, 4, 8, 6, 7, 2, 0. Of course it is not a random, it is a pseudo-random sequence. But this is somehow how we produce random numbers, and we want a length of this sequence to be in the order of like 1,000 or million or billion something. Okay, we don't want this in the length of 9 or something. Okay, we want it bigger. Okay, this is just to introduce you. Okay, now I want to show you this power of randomness. Uh, Doing this example. Okay, so for example, if we want to find the value of pi, for example. Sorry.
Can we take some questions? that they have so far before you move ahead.
Oh, sure. Okay.
Okay, so if any of you have questions, please unmute and ask.
Hey, hi Parth.
Hi.
So can you give us few examples of like how, where, and how we would use stuff like randomness or say MC, Monte Carlo simulations in uh, real
Okay.
life?
Okay. So you're asking where we will use random numbers and where we will use Monte Carlo simulations, right?
Right.
Okay. To give you an example of random numbers, well, it is everywhere. For example, if we use statistical mechanics, we do random walks and those things. So we simulate the molecules in a box. We simulate, for example, if we have a solar system, we build a solar system, artificial solar system where we got the planets, and we want to know what is the behavior of the system. And we got to do this Lagrangian kind of things, but we do need random numbers there. Now, when you are asking Monte Carlo things, okay, Monte Carlo has actually this thing as we do is we use it for integrals, to evaluate the integrals, okay, which is very important. For example, in quantum mechanics, um, uh, uh, when we do quantum mechanics, we want to find the Hamiltonian of the system, right? Okay, yeah. Uh, what is the Hamiltonian of the system? Hamiltonian of it, average Hamiltonian is equals to actually the uh, the wave function times the
Mhm.
this h of x and h. You know this, okay? This is a simple integral. It looks simple, okay? But here's a problem. Sometimes we got delta functions. Sometimes we got these wiggly wave functions, okay? And we know that we want to solve it because it gives us eigenvalue, which is actually the observable, okay? So we want to solve
Mhm.
this kind of integrals, and to do this, we need Monte Carlo. You see that?
So it's essentially like you are
Okay,
solving
okay,
this
wait. Okay,
approximations
sorry.
many
Let me
many
give you
times
an
and then you are averaging it.
sorry.
Okay, so it is like you are solving this numerically with low precision many times and then you're averaging it, sort of, so to speak.
Oh yeah, okay.
Is that
So
how?
what we're doing is, yeah, this is sort of how we work. We take a canonical ensemble, okay, and we what we do is we assume that this is all in equilibrium, okay. So imagine
Mhm.
one box. We got a gas within it, okay, and everything is
Mhm.
thermally equilibrized, okay. And the way you say it, we want you did again and again and again. Statistically you do 1,000 times, and when then you average it and then you find it. But to do that, you have to initialize your system, right?
Yeah,
Okay, and most of the time we use random initialization, and that's why random numbers are
right.
important.
So that's why
Yes.
random numbers are important. Okay, great.
Yeah. Okay.
So in that way we can use this to validate our models as well, right?
Sorry.
So in like by extending this principle, we can use Monte Carlo to validate our models also, right? To give some statistical robustness to
Oh yeah,
say
yeah,
your
yeah. Yeah, to validate the truth of some some bigger samples and those kind of things. Yeah, we can use that.
yeah. So like if I were to say I throw a ball and it falls, it goes to a certain height and it falls at this place. Now I can use
Okay. Sorry, I couldn't hear you.
Monte Carlo simulations to statistics from. Oh, sorry. So if I were to just take a ball, small ball, throw it, just throw it with my hand, and if I do this experiment enough number of times, I will be able to calculate ballistics or projectile motion from that, right? From that experiment.
Oh, Okay.
I think
Actually,
my voice
the
is
system
breaking.
you described, is my voice breaking? Anybody have a voice problem or my problem?
No, we can hear you fine. You can go ahead.
Okay. Jishnu, can you hear me?
Able to hear me? I can now I can hear you. James here?
Jishnu,
I,
you got some voice issues.
yeah. Sorry. My internet is really slow. So
Okay, Vikrant, you
I
had,
can see your screen though.
or Parth, you can give the answer.
Sorry,
Do you want to answer Jishnu's question, or do you
but
want?
I don't know. I didn't hear his question. Sorry.
Okay, Vikrant, can you ask your question?
All right. Am I audible?
Yes.
All right. So I had a little more basic question. I just sort of got into numerical techniques recently. So
Okay.
I'm sort of new to all of this. And so my question is, why should I choose Monte Carlo integration over the other integration techniques that I've learned, like the trapezoidal rule or
Yeah.
I don't know,
Okay.
something like
Okay.
the Newton formula, something like that.
Yeah. Beautiful question. Okay. So here's the thing. Let me show this. Where is it? Okay. You know that when you want to use your trapezoidal rule and all those things, you said Simpson rule, and there is another very beautiful quadrature called Gaussian quadrature. I love it. Okay, we don't have time to discuss it. I can spend like 1 hour on that, but it's beautiful. Do you guys know about Gaussian quadrature, Vikrant?
No. I'm still new to all of this. So
Okay, no worries. Okay, then let me just give you the perspective only from the trapezoidal rule, which you already know, and the Monte Carlo.
yes, that'll help.
Okay. Now see here. Suppose I want to integrate over one-dimensional function, right? Okay. Uh, um, to do that, you need to evaluate this function at n points. Do you see that? Okay. So you have to evaluate this function at n points in one dimension. So suppose you got a square domain. Okay. Uh, um, okay. How do I? Suppose you got a square domain like this in multi-dimension. Okay. Uh, then then you have n number of points here, n number of points here, n number of in third dimension, in fourth dimension. You see that in every dimension you get n number of points. Okay, so I say n number of points in each dimension. So total number of nodes I have to evaluate the function at is capital N. Okay, now uh, uh, before we studied the error and machine epsilon and all those, okay, it introduces an error, and again within this definition of Riemannian sums, we have an error of order this order of n minus 2, 1 upon n squared. Okay, um, uh, so in n dimension, the trapezoidal rule, which you already know, the error of that thing is n to the power minus 2 upon d. You see that? And the Monte Carlo is under root minus n. This is very beautiful. Do you see this? This is independent of small d, where d is the dimension of the domain of your integral. You see? So in trapezoidal
So
rule, what
whatever the
happens
number
is,
of dimensions, the error is always the same, is it?
no, here's the thing. In trapezoidal, as you increase the dimension of your integrand, okay, the error increases rapidly, okay. And in Monte Carlo, it only and only depends on how many number of nodes you are taking and how many number of Monte Carlo simulation you are doing. So it doesn't depend on which dimension you are doing this simulation. Yeah.
Okay, got it. So it's because of the error difference that we prefer Monte Carlo over trapezoidal, is it?
Oh, no.
Also the computational cost.
Right.
Of course,
Okay.
computational cost, but there is this another thing. We got some Ising models for magnetism, ferromagnetism, and in next session we are actually going to do the molecular dynamics. So if you are interested, attend that, where I will actually come to this and say, okay, that there is something beyond Monte Carlo. Okay, Monte Carlo is not the end. Okay, we need to do so many things beyond Monte Carlo. There are better things than Monte Carlo. So, and the reason why we are using Monte Carlo over trapezoidal, uh, again, we are not using it for all dimension. Do you see here? If I put d equals 1, for example, if I put d equals 1, what is the total error in d dimension? Order of n to the power minus 2, which is 1 upon n squared. Okay, and here it is under root n. So this error is less than this Monte Carlo. So trapezoidal error is less than Monte Carlo in one dimension. So it depends on your function in your situation that which method you want to use. So if you're doing one dimensional integral, definitely use the trapezoidal rule and not Monte Carlo. But if you go to higher dimensions, and we definitely need to go higher dimensional if you are simulating physical phenomena like some gas or solid or some quantum mechanical phenomena, we need to do higher dimensional things, which I just showed you, Hamiltonian thing. Okay, for that we use Monte Carlo and not trapezoidal.
Okay.
Or any other.
Thank you. That was good.
Okay.
Thank you.
Okay. So I move forward.
Yeah.
Okay. It's been too long. I will try my best to cover it in like less than 10 minutes. Right. Okay. I have written code for every single method I have introduced here, except these two functions which you have to write. For that, I have written the pseudocode kind of thing, so you get the idea how to write it. And also, okay. Now here's the thing. In Monte Carlo, what we do is just like listener said. Is my internet stable? Can you guys hear me? Hello.
Yeah. I think I can hear you at least. I don't know about others.
Okay. Thank you. Okay. So let's to make it all simplistic and imagine it properly, go to one dimension. And I want to introduce you Monte Carlo in one dimension and not higher dimensions, because actually we do it in higher dimensions, but to get the intuition, let's do it in one dimension. So we got a one dimensional function f of x, okay, and xi's are the points which are in the domain in which we want to evaluate the integral, right? And these xi's are actually randomly chosen. This is very much important. Okay, and from which distribution? Okay, this is another thing. From where we choose these random numbers? From the distribution. Okay, so here we did this random number thing here. Okay, we use this equation called LCG, linear congruential generator. Okay, and it will give us these numbers. And if we produce large enough numbers, and we do some computation on that, and we can figure out which distribution it is giving us. You see that? Okay, and if it is giving us average of 0.5, and okay, we do two kind of things in there. to test that if the given distribution is good or not. Okay, so first thing we need to do is average, find the average of that distribution and the variance of it. Variance is like how much spreaded it is from the mean of or average of the distribution. Okay, the less spreaded it is, the higher it has to find to be at the average, right? And what is the use of this? Then we know that within certain domain we can generate random numbers more probably than other domains. And why we want to do this? Because oh, okay. Before going there, let me give you a short exercise here. Okay, I want to calculate a value of pi. Okay, so imagine a circle here, and here is a square which is tangent to these four sides. Okay, uh, how to calculate this using random numbers? Okay, no geometry, no algebra, nothing, only statistics and random numbers. How do you do that? Okay, we it is very well known as a dart problem. uh, um, what we do is we throw darts on this board. We imagine a board and draw a circle, um, and we throw the darts on it randomly anywhere. So we got one point which is either within the circle or outside the circle. You see that? And if I throw large enough darts, then I can count that how many darts did I send in within the circle, and how many total number of darts did I throw at the board. Okay, and if I take the ratio of um, a number of points within the circle upon how many darts did I actually throw it, this ratio should be proportional to the area of circle upon the area of square. You see that? Okay, so I'm taking this radius as 1, so pi r squared, so r is 1, so this is the area of circle, and these 4 okay, which is actually the area of square. Okay, okay, 4r, sorry. Okay, so circle upon square equals to this number of inside points upon total points. And I do this so many 3, 4, to the power 5 times. I do this. So I generate a random number x. So I say, okay, with the domain, generate an x random number here. Okay, I have a random number here, and then I generate another here, then y, and I say, okay, is this within circle or not? And you know how to calculate it. Just find the distance x squared plus y squared. Is it less than 1 or not? 1 is the radius, right? And by doing this, it is surprising that when we do this equation, we actually do get the pi here. Okay, I don't know why my again got hanged. What's going on? Okay. It's not that many points. It should come. Okay, let me refresh it. Okay. Um, do you see this? It comes 3.14576 if I do it 10 to the power 5 times, and error is something order of -3. And if you want to see the convergence, I can just and do this, but let's not waste time on that. Okay, so you get the power of randomness. Okay. um, okay. um, okay, so the question of Monte Carlo, we have this domain. We choose random numbers randomly. Randomly choose points on this domain. We evaluate the function at those points. Okay, and this is what it represents. And J represents the jth Monte Carlo simulation. So if I do the first, if I take some random numbers here, and I evaluate the function there, I find the average. Okay, this is first Monte Carlo simulation. I do it again, and I do it again and again and again m times. Okay. Now, okay. Sorry. Okay, I take m random points and I find the average. So this is one Monte Carlo simulation, and this is one Monte Carlo simulation, and I do that n times. Okay, here is the error. Let me solve it. It should be n here. Okay. Okay. You see that? I take m random numbers in the domain. I find average of it. This is first Monte Carlo, and I do Monte Carlo again and again n times, and then average it, and then I get the average of the function. This is in a sense what Monte Carlo is. Okay, but there are many complicated and sophisticated version of Monte Carlo, which we don't have time for now. Okay, which I wanted to, but we don't have time. Okay. So what are the complications? If you want to write the code here, you can write here for Monte Carlo using okay, which is very easy, I think. Okay, based on what I have written here, you can get an idea what to do. Okay, I just showed you this, right? Yeah. Okay. First, don't get do the without evaluating at all points. We just have to evaluate at certain points, but we still don't get that rapid convergence. You see that? And we need to improve upon that. And how do we improve it? We improve it by introducing new distributions, new PDFs, probability distribution functions for the given functions. And we okay, so before here, what we did here, we took a normal distribution for doing these all things. Okay, but if we want to do better, we need to choose an appropriate distribution based on what the shape of a function is, and you do that. And another problem is the conservation of probability. If you have studied quantum mechanics, you would know this. Okay, but in short, I would say it is like we got some infinities in our computation. Okay, how do we how do we manage that? How do you probabilities in so let me show you. Here is a function. We want to evaluate the graph of this, right? Of course, you know that you don't want to calculate from there. We want to calculate only this within this, and you know that the probability distribution function, the integral of it should be 1 because it is probability, right? Okay. Now we want to change the variable from this to another variable. Why? Because of its shape. So certain shapes are there, and we want to build a PDF based on that and change the variable. Okay, and then we use this conservation of probability, that if within this space, if this probability is 1 in this within this constraint, and if I change the variable, go to the new R space, will the probability still be valid? And we want it to be valid, of course. Okay, so we need to use those constraint, those kind of things. Okay. Okay. The thing is, we just took samples here. I just told you we took random variables randomly from normal distribution. Okay, but what is the best way to choose the samples from our population? Okay, so we need to improve those kind of things, and then we can say, okay, we have done something beyond Monte Carlo, but now we have done Monte Carlo. Monte Carlo is, and if you want to read further, here is the reference. Okay, and that is all for today.
Hello, Pat.
Hi. Yes.
Am I audible?
Yes. Yes.
Okay. Yeah, so some of them want to leave right now. So we were wondering if we can continue this in the second session because it's getting slightly
I
late.
just finished it.
Yeah, you
I
can take
just
another 5 minutes and then finish it. And if there are any questions, guys, or comments, please put it on the chat box so he can address it over the next 5 minutes, or you can connect with him on Discord as well. Okay.
Okay. Yeah. Okay then, guys, it's done. Okay, we'll meet you soon on next Saturday. Um, okay, let me show you what we'll be doing so that you get an idea. Okay. Okay, we will be doing what we'll be doing is we will be okay. Before you come to the next session, I request you, or at least suggest you, to have little bit reading on this kind of things, like what is equipartition theorem, and intermolecular pair potentials, and because we will be using it to simulate our molecules, and what we will be simulating is argon gas within one volume, and we will be using a little bit Monte Carlo and a little bit of other techniques, and most of it will be actually statistics. So yeah, next Saturday. Thank you, guys.
Hey, thank you, Parth.
Okay. Yeah, Justin, thank you.
Yeah. Thank you, Pat. Yeah.